Welcome back to Mathematics class, Continuity and Differentiability Part 2. In the previous part, we mainly discussed the continuity of a function. Today we are going to discuss about the differentiability of a function. First we find the differentiability at a point. How to define the differentiability of a function at any point in its domain. Let f of x be a real valued function, that is, range is subset of real number defined on closed interval ab. Let c be any number on open interval ab. Then f of x is differentiable at x is equal to c. Then limit x tends to c, f of x minus f of c divided by x minus c exists finitely. That is, a function is differentiable at a point c means the limit at x tends to c exists. Limit of a function exists at a point means its left limit and right limit exist and they are equal. How to find left and right limits? To get left limit, put x is equal to c minus h, and to get right limit, put x is equal to c plus h. That is, limit h tends to 0, f of c minus h minus f of c divided by c minus h minus c. Put x is equal to c minus h, that is the left limit. For right limit, put x is equal to c plus h, that is, limit h tends to 0, f of c plus h minus f of c divided by c plus h minus c. They exist and equal, then only the limit at x is equal to c exists. We can cancel c plus c minus c cancel here. Here also plus c minus c get cancelled. Then it becomes limit h tends to 0, f of c minus h minus f of c divided by minus h, which is equal to limit h tends to 0, f of c plus h minus f of c divided by h, which is the required condition to be a function f of x is differentiable at the point c. Which is the condition? Limit h tends to 0, f of c minus h minus f of c divided by minus h equal to limit h tends to 0, f of c plus h minus f of c divided by h. Then we say that the function is differentiable at the given point x is equal to c. Geometrical interpretation of differentiability. For this, we consider a function y equal to f of x. Let P is a point on the curve where c, f of c is the coordinate of P. H be small increment on c or x. Then the point is very close and left of P is q. Then coordinates of q are c minus h, f of c minus h, and the point very close and right of p is r. Then coordinates of r c plus h, f of c plus h. Slope of pq, where p and q are the points, p c, f of c, and q c minus h, f of c minus h. We know that slope is y2 minus y1 divided by x2 minus x1. Therefore, slope of PQ can be written as f of c minus h minus f of c divided by c minus h minus c. Here, plus c and minus c get cancelled. Then it becomes f of c minus h minus f of c all divided by minus h. As h tends to 0, q tends to p. When h tends to 0, then q tends to p. So slope of the pq can be written as limit h tends to 0, f of c minus h minus f of c all divided by minus h. In the figure, when q tends to p, then chord PQ become a tangent at P, then PQ become, chord PQ become a tangent at P. Therefore, slope of chord PQ become equation of the tangent. Then equation of tangent at P can be written as limit h tends to 0, f of c minus h minus f of c divided by minus h. Slope of chord PR from the figure PR, chord PR, which is equal to f of c plus h minus f of c divided by c plus h minus c and plus c get cancelled, which is equal to f of c plus h minus f of c all divided by h. As h tends to 0, r tends to p, then slope of PR become limit h tends to 0, f of c plus h minus f of c all divided by h. When r tends to p, then chord PR become a tangent at p. Therefore, this expression limit h tends to 0, f of c plus h minus f of c divided by h become equation of the tangent at p. Equation of tangent at p, which is equal to limit h tends to 0, f of c plus h minus f of c all divided by h. That is, derivative of a function exists at a point means that it has unique tangent at that point. Differentiability in an interval. There are mainly two intervals, open interval and closed interval. A function f of x is said to be differentiable in given open interval AB means that it is differentiable at all the points in open interval AB. A function f of x is differentiable in given closed interval AB. Then first one, f of x is differentiable in all the points in open interval AB, and at the endpoints limit x tends to a plus f of x minus f of a by x minus a and limit x tends to b minus f of x minus f of b by x minus b exist and finite. That is, at the endpoints, right limit of a and left limit of b exist finitely. Next we pass to the session differentiability and continuity, the interconnection between differentiability and continuity. If a function y equal to f of x is differentiable at x is equal to a, then it is continuous at x is equal to a. That is, differentiability means or implies continuity. That means if a function is differentiable, implies it is continuous. Next we pass to the proof of given statement. For this, let y equal to f of x is a differentiable function at x is equal to a, which implies limit x tends to a, f of x minus f of a divided by x minus a exists and finite. This definite value can be taken as f dash a and consider it as equation 1. Now we take the function f of x as f of x minus f of a plus f of a. We add and subtract the same value f of a. Then divide the first term by x minus a and multiply by same number. Then we can write it as f of x minus f of a divided by x minus a into x minus a plus f of a. Take the limit on both sides, that is limit x tends to a, f of x is equal to limit x tends to a, f of x minus f of a divided by x minus a into x minus a plus limit x tends to a, f of a. That's equal to limit of the product means limit of first function into limit of second function. What's the limit? Using the equation 1, which is equal to f dash a. That's equal to f dash a into, if we put x is equal to a, this becomes 0 plus limit of the constant equal to constant itself. Therefore, limit x tends to a, f of x equal to f of a, which implies the function is continuous. That is, any differentiable function is continuous at that point. What is it? Any differentiable function is continuous at that point. In simply, differentiability implies continuity. What is the converse of this statement? Now we prove that a function is differentiable, then it is continuous. Differentiability implies continuity. Then what is the converse? Continuity implies differentiability. The converse is not true. That means if the function is continuous, then it may not be differentiable. This can be proved through an example. For this, we consider the function f of x is equal to mod x. We know that mod x is equal to minus x if x less than 0 and x if x greater than or equal to 0. First we find or check the continuity of the function at x is equal to 0. For this, LHL equal to limit x tends to 0 f of x. What is f of x here? Minus x. When x equal to 0, minus x is also 0. Then we goes to RHL, right hand limit, limit x tends to 0 plus f of x. Here f of x is x, that's again equal to 0. At x is equal to 0, f of x is equal to x and f of 0 equal to 0. Therefore, LHL equal to RHL equal to f of 0. Therefore, f of x is continuous at x is equal to 0. Then the second part, we have to check the differentiability at x is equal to 0. The left hand derivative by formula limit x tends to 0 minus f of x minus f of 0 divided by x minus 0. Through the left side, f of x is equal to minus x, that is limit x tends to 0 minus x minus, when x is equal to 0, f of x is equal to 0 divided by x, that is limit x tends to 0 minus x by x, that's equal to minus 1, limit of the constant equal to constant. Then what about right hand derivative? That is by formula limit x tends to 0 plus f of x minus f of 0 divided by x minus 0. Right means or right hand derivative means x greater than 0. When x greater than 0, mod x equal to x. So this can be written as limit x tends to 0 x minus 0 divided by x, that is limit x tends to 0, x by x, that's equal to 1. Here left hand derivative not equal to right hand derivative. Therefore, f of x is not not differentiable at x is equal to 0. Therefore, f of x is not differentiable at x is equal to 0. That is, continuity not implies differentiability. That is, if a function is continuous at the given point A, not implies it is differentiable at x is equal to A. Show that f of x is equal to x minus 1 if x less than 2, 2x minus 3 if x greater than 2 is not differentiable at x is equal to 2. First we find left hand derivative by formula limit x tends to 2 minus f of x minus f of 2 divided by x minus 2, which is equal to limit x tends to 2. 2 minus means x less than 2. When x less than 2, the function is x minus 1. So f of x become x minus 1 minus. Then x is equal to 2. The function is 2x minus 3. Then f of 2 equal to 2 into 2 minus 3, that is 4 minus 3 equal to 1. Instead for f of 2 we can write 1 divided by x minus 2. That's equal to limit x tends to 2, x minus 2 divided by x minus 2, that's equal to 1. We find right hand derivative at x is equal to 2. By formula it is limit x tends to 2 plus f of x minus f of 2 divided by x minus 2, that is limit x tends to 2. 2 plus implies x greater than 2. When x greater than 2, f of x is 2x minus 3. So instead for f of x we can write 2x minus 3 minus f of 2 is 1 divided by x minus 2. That is limit x tends to 2, 2x minus 4 divided by x minus 2. That is limit x tends to 2, 2 into x minus 2 by x minus 2. X minus 2 get cancelled. That is limit x tends to 2, 2, that's again equal to 2. Here left derivative is 1 and right derivative is 2. Therefore LHD, left hand derivative, not equal to right hand derivative. Therefore f of x is not differentiable at x is equal to 2. We move to next question. Show that f of x is equal to mod x plus 1 plus mod x minus 1 is not differentiable at x is equal to 1. Here the function is mod x plus 1 and mod x minus 1. So we split or find the value separately. Mod x plus 1 equal to minus of x plus 1 if x less than minus 1 and x plus 1 if x greater than or equal to minus 1. Mod x minus 1 equal to 1 minus x if x less than 1 and x minus 1 if x greater than or equal to 1. From this it is clear that mod x plus 1 and mod x minus 1 divert at or split at minus 1 and 1. So the given function f of x can be written as minus of x plus 1 plus 1 minus x if x less than minus 1, x plus 1 plus 1 minus x if minus 1 less than x less than 1, and x plus 1 plus x minus 1 if x greater than or equal to 1. That is, f of x is equal to minus of x plus 1 become minus x minus 1. Then plus 1 and minus 1 get cancelled. Minus 2x if x less than minus 1. Plus x minus x get cancelled. 2 if minus 1 less than x less than 1. Here plus 1 minus 1 get cancelled. 2x if x greater than or equal to 1. That is, the given function f of x can be rewritten like this. The left hand derivative LHD by formula limit extends to 1 minus f of x minus f of 1 divided by x minus 1. That's equal to limit extends to 1. When x less than 1, 1 minus means x less than 1. Here the function is 2. F of x become 2 minus f of 1. When x equal to 1, the function is 2x. Then it become 2 into 1, that is 2 divided by x minus 1. That is, limit extends to 1, 0, that's equal to 0. Then right hand derivative, that is limit extends to 1 plus f of x minus f of 1 divided by x minus 1. 1 plus means x greater than 1. When x greater than 1, f of x is equal to 2x. Then this can be rewritten like this. Limit extends to 1, 2x minus 2 divided by x minus 1. That is, limit x tends to 1, 2 into x minus 1 by x minus 1. X minus 1 get cancelled, that's equal to 2. Here, left derivative is 0 and right derivative is 2. That is, LHD not equal to RHD, which implies f of x is not differentiable at x is equal to 1. Let's find out the second part of continuity and differentiability here. In the next part, we are going to discuss derivative of the function. Thank you for watching my videos. Thank you.